Okay, I'm going to do a couple problems here. I'm going to solve number 9 and number 10 on worksheet 4. First, number 9, it asks you to determine the final velocity of the roller coaster assuming a 10% loss to friction. Well, first, let's define our system. Since we do have a car and it's got some gravitational potential energy, we have to include the earth. And since we have friction, I'm going to want to include the track or the rail or whatever it's on. And so there's going to be a 10% loss to friction. Well, I'm starting out with zero velocity, so I don't have any kinetic energy. So it's all in the form of gravitational potential. I'm going to use my 4 bars there. There's no elastic energy because there's no spring involved. And at the end, I'm going to have assuming, as it says here, I'm down to my zero gravitational potential energy point. I will have zero gravitational potential energy, but I will have some kinetic energy. 90% of the gravitational energy will have been converted to kinetic, and 10% will be thermal, okay, because of the friction. So basically, I've got UG equals K plus U thermal, okay? And they told us this was going to be 0.1 of what we started with, which was the UG here. And that's where I got, you know, my 90% from. If I subtract 0.1 from 1, I get 0.9 UG equals my kinetic. So 0.9 mg times my change in height equals my kinetic energy, my 1/2 mv squared. And I really don't need to know the mass of my roller coaster, even though they gave it to us. So V is going to be equal to the square root of 2 times 0.9 times g delta h, which is 1.8 times 10 times 5. So let me go offline for just a second here and I'll do that calculation. And I get 9.48 meters per second, or 9.5 to 2 sig figs. So again, that's a 10% loss in gravitational potential energy. So when they say assuming a 10% loss to friction, that's 10% of what you started with. And we started with all gravitational potential. So that's how I'd figure that one out. The next one that was asked about was number 10. The moon could be an ideal spaceport for exploring the solar system. A moon launching system could consist of a magnetic railgun, wow, that shoots items into moon orbit. How much energy would be needed from the railgun to get a 10,000 kilogram capsule into an orbit that's 100,000 meters or 100 kilometers above the moon's surface? Now, in this one, they assume that the moon's gravitational field strength is constant at 1.69 newtons per kilogram. This would be, I would challenge that and say this might be one where we would want to use this formula here, but that's not how this was intended to be worked. So, because they gave you a constant value of this, so I'm not going to make it more complicated. And they wanted to get this thing moving at 1,700 meters per second. So the railgun is going to do work because it's outside of the system. So how many joules is required? You start out with no kinetic energy, no gravitational potential energy. So a bunch of work is being done. Oops, that was pretty good. I don't know, we'll call it 4 blocks worth of work. And we end up with let's say 2 blocks of kinetic and 2 blocks of gravitational potential energy. Okay, so we don't have any spring energy in the system at the end. There's no atmosphere on the moon, so we won't lose anything to thermal energy, even though you might have some, well, with magnetic railguns, you probably don't have any friction either because their 2 surfaces probably aren't in contact. So work is going to be equal to the amount of kinetic energy using the terminology up above instead of our book variables. So 1/2 mv squared plus mg delta h. The delta h is 100,000 meters, because you have to remember to keep that in terms of the meters. We have a 10,000 kilogram, this is 10,000 kilograms. This is 1.6, and again, assuming it's constant. I actually did a quick calculation to determine how different the value of G would be on the moon at 100,000 kilometers. At the surface of the moon, it's actually 1.62 newtons per kilogram, but at 100,000 kilometers, it goes down to 1.44. So there is enough of a difference where the gravitational potential energy would not be as high at that altitude. So I will ask you, what do you think that does to the amount of work required by the railgun? Does that increase the amount of work it has to do to get something up to 100,000 meters at this speed, or does it decrease it? Anyway, back to our problem. This is 10,000. This is 1,700, and then 1/2. So just plugging everything in, you don't need me to write all that out again. Solving for work, doing all the algebra on the right-hand side. The answer I get, and I'll go offline real quick. Okay, so what I got was, sorry, I'm making this really messy. I came up with about this much in kinetic energy, about this much in gravitational potential, assuming a constant gravitational field strength of 1.6, and I come up with that much work. Okay? If you have any other questions on this worksheet, let me know, and we'll go over them, or I'll make another screencast, and I will see you tomorrow.